Hello and welcome back to one academic's journey to reteach himself organic chemistry. Today we're going to be talking about anomers, epoxides and peroxides. First up, a quick reminder that stereoelectronic trends are what influence bond strengths. We're going to be talking about bonds being formed and bonds being broken. For sigma bonds, which are typically comprised of sp orbitals, bond strength comes down to proper alignment of those orbitals, as well as similar energy levels, which might mean atoms of the same type, or that electron density isn't being drawn away by a third atom. This also applies to pi bonds, which often relates to p orbitals. In the last video, we briefly talked about hyperconjugation, which is delocalization of electrons drawn from a sigma bond of some sort of leaving group that's adjacent to a carbocation in a syn-plane orientation. Provided these two orbitals are correctly aligned, the electrons are delocalized over both, meaning that they can slip across to form this new double bond, releasing the R group. If we think about the MO diagram, because the sigma orbital to the R group and the empty p orbital of the carbocation are correctly aligned and similar in energy, we can hybridize these two orbitals together, creating a new bonding and anti-bonding orbital. And if we compare the energy of populating the anti-bonding orbital before and after, we can see that the energy needed to promote an electron up to the anti-bonding orbital is considerably more before hybridization than for the newly hybridized orbital shown here. So what that means is the energy that you actually need to release this R group, shifting the electrons into the double bond, has gone down with hyperconjugation. Now there's a similar idea for negative hyperconjugation. So where before we were talking about a carbocation, now we're going to be talking about a similar reaction with a carbanion, that being a negatively charged carbon group. Where previously the orbitals were adjacent to one another, negative hyperconjugation requires anti-planar orientation of the orbitals. So effectively, this is the orbital that will break, and the negatively charged lone pair is on the opposite side. And the mechanism whereby it works is this negatively charged orbital will stabilize the anti-bonding sigma orbital for the R group. So here we have the regular bonding orbital. If we draw out the anti-bonding orbital, we create this new lobe of electron density, which is directly adjacent to the non-bonding electron pair. It can then delocalize across, stabilizing this anti-bonding reaction and making elimination of this negatively charged R group lower in energy. This creates a similar double bond at the conclusion of the reaction. So thinking about delocalization of these lone pair orbitals, there's a couple of chemical phenomena that we can explain using this idea. So the first one is, which of these two conformers would we expect to be more stable? And just looking at the two, it's likely you would probably pick the trans conformer as being the more stable of the two. And the reason for that comes down to a steric argument. If we think about these fluorine groups, which are covered in lone pairs themselves, were we to look at the cis conformation, we might expect there to be steric clashes between both fluorine groups. But in reality, when we look at the experimental data, it's actually the cis conformer that is the more stable of the two. And this comes down to the same idea as in the previous slide. If we draw out the anti-bonding orbitals between the nitrogen and the fluorines, and then look at the position of the lone pair orbitals, we can see that when we draw out the anti-bonding orbitals, the lone pairs can delocalize into them, stabilizing them. And this can occur on either side of the molecule. Now this doesn't necessarily mean that the nitrogen to fluorine bonds are going to break. It can be happening spontaneously for a small percentage of the time. All we're considering is how the electrons are delocalizing around the molecule. Because the more delocalized those electrons can be, the more stable the molecule will be overall. This is one of the ideas we get out of drawing resonance structures for molecules. The more resonance structures there are, the more stable that molecule typically is. So because this molecule has better alignment and thus more delocalization of electrons, it's more stable than this misaligned conformer that doesn't benefit from those interactions. This idea is also carried over when we talk about the anomeric effect in sugars. Here we have two sugars. They're in an equilibrium because they can adopt an open chain form and close again, randomizing the conformation shown in the red box. What we would expect is this beta conformation, where we have the alcohol in the equatorial position, to be more stable than the alpha version, where the alcohol is pointed downwards in the axial position. But this effect isn't as pronounced as you would expect it to be. And the reason for that comes down to something called the anomeric effect. Breaking it down, the anomeric effect stabilizes groups in the axial position when they are adjacent to the lone pair of an oxygen, or really any lone pair donor. This can seemingly overpower the preference of larger functional groups to be in the equatorial position, like we would usually expect. And again, this comes down to a stereoelectronic effect. And once more, we need to think about stabilizing the anti-bonding orbitals in the position adjacent to the lone paired donor. So looking at the axial version of the molecule, if we draw out the anti-bonding orbitals, like so, we can see that the oxygen lone pair is correctly aligned to delocalize and thus stabilize this anti-bonding interaction. If we look at that same group in the equatorial position, those anti-bonding orbitals are not stabilized in the same way. So the molecule on the left is missing out on that stabilizing interaction, whereas the molecule on the right benefits from that additional interaction. And that's what provides the anomeric effect. As I alluded to before, it's not just for oxygen, other electronegative atoms benefit from the effect as well. So if we look at this molecule shown down here, we have two chlorine atoms, both of which are adjacent to an oxygen, that can be the lone paired donor. One is positioned in an equatorial position, the other is shown in an axial position that could benefit from the anomeric effect. And if we look at those two chlorine to carbon bonds experimentally using something like X-ray crystallography, we can measure out the length of this bond. And indeed, the axial chlorine bond is longer, meaning that that bond is being destabilized, and that is occurring due to the anti-bonding orbital receiving stabilization from the adjacent lone pair from the oxygen. Given these are similar in energy and they're correctly aligned, we can draw an MO diagram showing hybridization of those orbitals. What occurs is the oxygen lone pair orbital drops in energy as it hybridizes with the anti-bonding carbon to chlorine orbital. This in turn creates a new anti-bonding orbital shown up here. Now if we compare the original carbon to chlorine orbitals, we can see that to promote an electron from this position up to the anti-bonding orbital, there's this amount of energy required, whereas after we hybridize, the amount of energy needed to jump from this bonding orbital up to the anti-bonding orbital has lessened. That means that this orbital is now easier to break than the other orbital, and we can see that in terms of a longer bond. So we can start to think about this in terms of named organic reactions, in particular involving esters. So if we think about the ester oxygen, it's sp2 hybridized and donates 2 electrons into this 4-electron pi system. That effectively locks the conformation of the R group and the lone pair into one of 2 positions, those being the E or Z conformants. This pi system also creates a barrier to rotation around this group shown here. So the S-cis conformer, where we have the ketone oxygen and the R group on the same side, this is the Z conformer and it's lower in energy versus the S-trans conformer, also known as the E conformer. Now the Z conformer, its low energy nature can't be rationalized just using a steric argument. Instead, this lone pair that does not participate in the pi system participates instead in hyperconjugation. Now, initially, when you think about the Z and the E conformers, you might think that regardless of which conformation occurs, that lone pair could participate in hyperconjugation. And that's true. So really it comes down to which antibonding orbital is more inclined to form. So looking at the Z conformer, this antibonding orbital arises between the carbon and an oxygen. These are different atom types. They're going to be different in energy, meaning that that bond is going to be weaker than the related E conformer, where we're comparing 2 carbons of similar energy. So the fact that the Z conformer is lower in energy comes down to the fact that this antibonding orbital is more likely to occur than this antibonding orbital. And that guides the lone pair of the oxygen into this position, creating this Z conformation shown here. Because this carbon-carbon antibonding orbital is less inclined to occur, the oxygen lone pair is less influenced by it, meaning you're less inclined to see this E conformer. Now if we expand the ester to think about peroxides. Here we have a reaction, peroxide group is here, it's reacting with an alkene, and we're forming an epoxide group over here. If we consider what bonds are going to break in this reaction, It's this oxygen to oxygen bond that's potentially going to break, as well as this carbon-carbon double bond. New bonds that are going to form include these two carbon-oxygen bonds making up the peroxide. With that knowledge of the bonds that are going to break and the bonds that are going to form, we can think about the antibonding orbitals that are relevant to the reaction, as well as the orbitals associated with the atoms where new bonds are going to form. So that gives us our LUMO, antibonding orbitals, and HOMO bonding orbitals. Now, there's two scenarios that could result in the products of this reaction. The first is the oxygen to oxygen bonds break, forming new bonds with the double bond. So sigma antibonding orbitals for the peroxide, and they're interacting with the pi orbitals of the alkene. Conversely, it could be that the pi antibonding orbitals of the alkene interact with the lone pair orbital of the oxygen. In the scenario on the left, the antibonding orbital interacts with the electron cloud of this pi bond, whereas on the right, the antibonding interaction of the pi orbital creates this mismatch in the phase of those p orbitals, and this aligns really well with the positive and negative lobes of this p orbital associated with the oxygen lone pair. Drawing it out, we can get this transition state for the reaction, and we also discover that for the alkene or the olefin, more electron donating groups improve the reactivity of that reagent towards the epoxidation reaction. If we now consider dioxiranes, so the peroxide form of acetone, similar starting material, identical product, we can come up with similar HOMO-LUMO interactions for the two states, but here there's actually interesting steric influences over the reaction that occur. So the number and the size of the R groups are going to influence the way that the reaction can proceed. So arguably, if the R groups are clustered on the substrate in this fashion, the situation below is going to be favoured, whereas if the R groups are clustered on one side of the substrate, the alternate scenario will be favoured. In both situations, the size of the R groups are going to impact the rate of the reaction, with smaller groups having the reaction go more quickly than larger groups. And that brings us to the She asymmetric epoxidation reaction. Ooh, stray hydrogen, ignore that. That shouldn't be there. But the crux of the reaction is, if we have a substrate like so, a protected sugar molecule, and ozone, we can epoxidize our substrate in a stereoselective manner. It works by taking this protected sugar molecule, adding ozone to convert the ketone group into an epoxide. One approach to the epoxide is blocked by this bulky functional group in the protected sugar, whereas position above the peroxide is relatively free. This enables the substrate to position itself in one of two ways, directly above the peroxide, enabling this peroxidation reaction to occur. So this is another one of these blends of sterics and stereoelectronics that leads to interesting chemical effects occurring. The reaction shows high enantiomeric excesses occurring when the substrate has a smaller R1 group and larger R3 group. So the smaller R1 group allows the substrate to sit further within this cleft over here above the epoxide, whereas the large R3 group keeps the proper orientation to deliver enantiomeric excesses. Moving on to the Baeyer-Villiger reaction. This reaction creates esters from ketones and can also be used to expand cyclic ketones to give lactones. The reaction occurs via this cryo-G intermediate, which is this zwitterionic peroxide-like species. So interestingly, insertion of the oxygen into our ketone creates an ester whereby the oxygen is biased towards the bulkier functional group. So for the reaction of this ketone with a methyl group and a tert-butyl group, you get a ratio of 150 of the tert-butyl ester versus 1 of the methyl ester. So it's very much sterically directed. If we draw the reaction intermediate, shown here, we can start to understand why that is. So the reaction occurs when a nucleophilic alcohol group, we'll call it, attacks the electron-deficient carbon of the ketone, creating this intermediate shown here. If we look at the favoured conformer of this transition state, we see that the larger, bulkier tert-butyl group aligns in antiplanar conformation to the newly formed epoxide group. Given this oxygen-oxygen bond is going to break, we can draw out the anti-bonding orbitals, and the sigma anti-bonding orbital is directly adjacent to the sigma bonding orbital of the tert-butyl group. So delocalization is going to occur like so. In terms of how the reaction proceeds, essentially the electrons in this sigma bond for the tert-butyl group slide over, creating this product shown here and releasing this carboxylic acid. You can see the movement of electrons shown in the arrows here. Another way of considering the reaction is, once the bulky peroxide attaches to the ketone, we want to orient the bulkiest ketone substituent directly away from it. We can look at the other disfavored conformation. So in this scenario, the tert-butyl group is closer to the newly attached peroxy acid, and that creates this steric clash shown here. Assuming this does occur though, the same reaction occurs, except this time the sigma bonding methyl group is correctly aligned to stabilise the sigma anti-bonding oxygen-oxygen bond, and it slips across to give this product at the end. Here's the explanation you'll find on Wikipedia. We have our peroxy acid shown here at the top. You want the largest ketone functional group to be positioned as far away from it as possible. This minimises the steric clash of the transition state. You can arrange it the other way, but this transition state is disfavoured and so occurs less often in the reaction. So in summary, there's lots of interesting stereoelectronic effects to consider for anomers, epoxide and peroxide reactions. Some key named reactions include the She asymmetric epoxidation and the Baeyer-Villiger reaction. Some of these reactions are probably best understood with the help of a 3D chemical model kit. If this has helped you, drop a comment, as I'm always interested in who you are and where you're watching from. Thanks for watching.